Hello again. So in this video we're going to look at just some more examples of solving related rates problems. And this first problem here is really an extension of the last problem in the previous video. So if you didn't watch that video, it's going to be, that last part of the previous video is going to be quite useful in solving this problem. Alright, so now would be a good time to pause and try this one out on your own. So the setup is exactly the same. Top of a board that is 10 feet long, sliding down a wall. The instant the bottom of the board is 4 feet from the wall, the bottom is sliding away from the wall at a rate of 2 feet per second. Now here's the different part. At that instant, how fast is the area of the region between the board, ground, and wall changing? All right, so if we start exactly the same, if we start with the same diagram, and we still know that we know what? At the instant the bottom of the board is 4 feet from the wall, we know that x is equal to 4. We know that dx dt is equal to 2 feet per second. But now we're not asked to find dy dt, which we already figured that out, right? We figured that out from the previous exercise. Now we're asked at that instant, how fast is the area of that region changing? We're asked to find some dA dt, where this region right here, right? That's our region A, and we want to find the change in that area. All right, so we've got to figure out an expression for the area in terms of those variables x and y. Well, area of a triangle, that's not too difficult. We learned how to do that in, I don't know, like 3rd grade or something. It's half times the length times the width. So I know that the area of that region is 1/2 times x times y. Let's calculate the derivative with respect to t. So then dA dt, let's think about this. X is a function of time, right? X is changing with respect to time. Y is changing with respect to time. So I'm going to have to use a product rule here. I'd have 1/2 of, differentiate the first, dx dt. Leave the second alone, times y. Plus, leave the first alone, x, times, differentiate the second, dy dt. So dA dt is 1/2 times dx dt times y plus x times dy dt. So I'd have 1/2 times dx dt is 2 feet per second. Now, we figured out on the previous exercise, and if you didn't look at that, you'll need to go back for the details. We also figured out that at that moment, y is equal to the square root of 84, or 2 root 21. And we figured out that dy dt, that was equal to negative 4 over root 21, and those would be respectively in feet and feet per second. All right, so dx dt times y, y is 2 root 21 feet, plus x, x is 4 feet, dy dt is negative 4 over root 21 feet per second. So now let's look at the units on these. Feet per second times feet, that's square feet per second. That's a change in area with respect to time, so the units look good. All right, so let's see. We've got 1/2 of 4 root 21 square feet per second minus 16 over root 21 square feet per second. Let's get a common denominator of root 21. So let me multiply by root 21 in both the numerator and denominator in the first term here. So then that's 1/2 of 4 times 21 is 84. 84 minus 16 over root 21 square feet per second. 84 minus 16, that is 68. So I've got 68, and then 1/2 of 68 is 34. So 34 over root 21 square feet per second. And so that's how fast the area of that triangle is changing at that moment. 34 over root 21, whatever that number happens to be. The units would be square feet per second. A rocket is moving vertically upward at a speed of 300 miles per hour. At the moment the rocket is 2 miles above ground, how fast is the angle of elevation increasing, as seen by an observer on the ground 5 miles from the launch pad? This would be a great time to pause. Try this one out. Draw a diagram. Relate the variables. Be careful, though. We're talking about an angle. Since we're talking about an angle, you're probably going to need to use trigonometry on this problem. All right. Now would be a good time to pause and try it. All right, so let's assume we have a nice situation here where we have a right triangle. A rocket is moving vertically upward at a speed, so the rocket's height is increasing. Let's call that h. Here's the ground level. Let's assume that h is, since it's moving vertically, it's at a right angle to the ground, as long as the ground is relatively horizontal. How fast is the angle of elevation increasing as seen by an observer on the ground 5 miles from the launch pad? So here's my triangle, and we know that this distance is 5 miles, and here's the angle. Remember, angle of elevation is if we're at the horizontal looking up, right? So that's the angle of elevation, from horizontal up to the point that we're concerned about. So there's my angle of elevation. So then how can we relate the variables theta and h? That's what we're trying to figure out. All right, and what else do we know? The rocket is moving vertically upward. dh dt is 300 miles per hour. At the moment the rocket is 2 miles above ground. When h is equal to 2 miles, how fast is the angle of elevation increasing? We need to find d theta dt. That's our goal. Let's find d theta dt. Well, let's see. If we think about this right triangle, and we have the angle theta, we have h is opposite the angle theta, and 5, this distance from the person to the launch pad is 5 miles. That's adjacent to the angle theta. So I can use the tangent ratio. So tangent theta is equal to h over 5. Let's calculate the differentials. d by dt, d by dt. All right, differentiating with respect to t, tangent theta. All right, applying the chain rule. Secant square theta by d theta dt. Now, h over 5, that's the same as 1/5 h. I am not going to apply the quotient rule here because the 1/5 is a constant. So I have 1/5 by dh dt. All right, let's see. Dividing through, we're going to solve for the d theta dt, so I'll divide through by secant square theta. Well, dividing by secant square theta is the same as multiplying by cosine square theta, because they are reciprocals. So then d theta dt is 1/5 cosine square theta dh dt. Now, I know dh dt, that was given as 300 miles per hour. I don't know cosine square theta. So I've got to figure out cosine theta. Well, at that moment, when h is 2, now if I think of cosine theta, cosine is the adjacent over the hypotenuse. So I need the hypotenuse. Apply the Pythagorean theorem. If the adjacent is 5 and the opposite is 2, applying the Pythagorean theorem, the hypotenuse would be the square root of 25 plus 4, the square root of 29. And each of these are in miles. So then cosine theta is 5 over root 29. All right, so then d theta dt is 1/5 cosine theta squared. The cosine would be 5 over root 29, and we need to square that. And that would be in terms of miles over miles, so the miles reduce out. And then dh dt, is 300. So then 5 squared is 25. Reduce that out with one of the 5s. So that would be 5 over 29 times 300. So that would be 1500 over 29. So now what are the units on this? Now, the dh dt is officially in miles per hour. But if we think of theta, we don't measure theta in terms of miles, right? We would measure theta in terms of a unit for an angle. In calculus, we don't use degrees. All the functions that we worked with, differentiating the sines, the cosines, the tangents, all that, it doesn't work the same with degrees. It's in terms of the radian measure. So the units on this would be 1500 over 29 radians per hour. Alright, let's look at another problem. A boat is being pulled toward a dock at a constant rate of 3 feet per minute by a rope through a pulley on the dock, which is located 5 feet above the deck level of the boat. How fast is the boat moving toward the dock when the boat is 15 feet from the dock? So it might look like, it's moving towards at 3 feet per minute. But that 3 feet per minute is offset. I'm going to draw a diagram for this problem to make sure that it's understood what my intention is. All right, so if here's the water level, all right, there's the water level. All right, and here's the boat. It's not a very useful boat. All right, and here's the dock. The rope is being pulled through this pulley that's attached to the deck level of the boat. And that distance is 5 feet. So, now that you have that understanding, try and solve the problem. All right, so here's how I would think of this. The boat is being pulled toward the dock at a constant rate of 3 feet per minute. So I'm going to say that, here's this rope, and the length of the rope is changing. In fact, I know that dr dt is -3 feet per second. And what we're trying to figure out is how fast is the boat moving toward the dock? Well, if there's the dock, there's that vertical dock position, here's a horizontal position relative to the dock. Let's call this x. We need to find dx dt. When the boat is 15 feet from the dock, when x is 15. Now, it should seem reasonable if we sort of think through this problem that if x is the horizontal distance from the dock to the boat, then dx dt should end up being negative. All right, so let's see. How can we relate these quantities? Well, if we assume that we have a right triangle, I can apply the Pythagorean theorem. I know that x squared plus 5 squared is equal to r squared. And so I'll differentiate with respect to t, the entire equation, yielding 2x by dx dt plus 0, because 25 is a constant, is equal to 2r by dr dt. All right, and I'm solving for dx dt. So dx dt is equal to r over x by dr dt. So let's see, do I have everything I need? I know x, I know dr dt, I don't know r. I need to find r. So I need to find r when x equals 15. All right, if x is equal to 15, then 15 squared plus 5 squared is equal to r squared. 15 squared is, let's see, 15 squared plus 5 squared, that's 250. So r squared is 250. That's 25 times 10, so r is the square root of 250, or 5 times the square root of 10, if we want to simplify that. And r would be in feet. All right, so then we could take that. So then dx dt, r is 5 root 10 feet over x. X is 15 feet. And then dr dt is -3 feet per second. All right, so let's see, 15. That's just that simplifies as just negative square root 10. So dx dt. All right, 5 times 3 is 15. 15 over 15 reduces out. So negative square root 10 feet per second. There's my dx dt. So one more problem. Suppose that two resistors are connected in parallel, and resistance 1 is 60 ohms. All right, so that symbol, that omega symbol, is represents ohms. All right, so that's a measure of resistance, and that's ohms. If R1 is 60 ohms and is increasing by 0.5 ohm per minute, and R2 is 70 ohms and is decreasing by 1.2 ohm per minute, find the total change in resistance. So now this is a tough problem. This doesn't rely on geometry. You would have to know something about resistance in resistors in an electrical circuit. And so this one, we'd have to know a formula beforehand to solve this problem. And so one thing that is known, that's been figured out, is that if two resistors are connected in parallel, then the total resistance is dependent on the individual resistances, but inversely. So here's the formula. The resistance is such that 1 over the resistance is equal to 1 over R1 plus 1 over R2. So why don't you take the problem from here and see if you can solve it. All right, we are asked to find the total change in resistance. I need to find dR dt. And I know a whole bunch of pieces. I know the individual resistances at that time, and I know how they're changing. But to find dR dt, I'm going to have to calculate d by dt of this entire equation, both sides. All right, so now each of these, 1 over r, that's the same as saying what's d by dt of r to the negative first power. All right, and similarly throughout this. All right, so then d by dt of r to the negative first, that would be negative r to the negative second dr dt is equal to then negative r1 to the negative second by dr1 dt plus minus r2 to the negative second by dr2 dt. So now I know everything except for r. I don't know r, and so I don't know r to the negative second. So I've got to do another calculation here. If 1 over r is equal to 1 over r1 plus 1 over r2, then 1 over r, at that moment r1 is 60 and r2 is 70, is 1 over 60 plus 1 over 70. We add those fractions. We know how to add fractions. We learned how to do that in elementary school. So then 1 over r, 1 over the resistance, ends up being 13 over 420. So that means then that if 1 over r is 13 over 420, then r is 420 over 13. All right, so then taking this equation, we now have negative r to the negative second. So that would be 420. Well, I guess what I would do is, just to make things simpler, let's clear out all the negatives. Let's take this equation. I'm going to multiply this entire equation by negative 1. That gets rid of all of the subtractions, makes life a little bit easier. So then r to the negative second dr dt is equal to r1 to the negative second dr1 dt plus r2 to the negative second dr2 dt. All right, so r to the negative second. If r is 420 over 13, so that would be 420 over 13 to the negative second times dr dt. That one we don't, well, that's what we're solving for. Now r1 is 60, So 60 to the negative second. dr1 dt is increasing by 0.5 ohms per minute. By 0.5 ohms per minute. Plus r2 to the negative second. That would be 70 to the negative second. And then dr2. R2 is decreasing by 1.2. Decreasing. So times a negative 1.2 ohms per minute. Alright, so now if you go through all of this and simplify this, and I assume you know how to use your calculator, we find that dr dt is equal to approximately negative 0.11. And let's think about the units. I didn't write all the units there, but the resistance is measured in ohms, and the time was in minutes. So it should seem reasonable that dr dt is, the units would be in ohms per minute. Negative 0.11 ohms per minute. Alright, so that completes the presentations on related rates. Again, you've got to practice these exercises. So go into the recommended exercises and do as many as you have time for in preparation for any quizzes or tests. Alright, have a great day.